All right. Hi, everyone. So last week I shared this paper, Does Knowledge Distillation Really Work? Which talks about how knowledge distillation does not always work as we expect it to. And this week I'm excited to share my paper, Knowledge Distillation Doesn't Really Work Yet. So let's get started. As a reminder, knowledge distillation is a model compression technique, and it involves training a smaller student model to match the predictions of a larger teacher model. My goal for this project was to successfully implement knowledge distillation with MNIST, and I expected the distilled student to be worse than the teacher, but better than the student alone. So let's take a look at the important equations. First, the softmax function takes a vector, usually some logits, and returns a probability distribution. It is usually the last activation function of a neural network. And the temperature parameter controls the entropy of the resulting probability distribution, where a higher temperature returns a higher entropy distribution called the soft predictions, and a lower temperature returns a lower entropy distribution called the hard predictions. Next, the Kullback-Leibler divergence and cross-entropy loss functions each take two vectors and return a distance, and they are often the loss function of a neural network. And these equations are important because the distillation loss equation is the weighted sum of the cross-entropy loss between the hard student predictions and the true labels, and the scaled KL divergence between the soft student predictions and the soft teacher predictions. So an alpha of 1 is just the cross-entropy loss between the student predictions and the true label, and an alpha of 0 is just the scaled KL divergence between the soft student predictions and the soft teacher predictions. So let's take a look now at the big picture. So during knowledge distillation, first, the teacher and the student each make a prediction. Then the distillation loss is calculated using the teacher prediction, student prediction, and the true label. And finally, the student is updated. Consequently, both the student and the teacher make a prediction and contribute to the loss, but only the student is updated. So let's get into the project. First, I loaded MNIST. I scaled the images and then split the data into stratified train, test, and validation subsets. Next, I created and trained the teacher, which was a simple convolutional neural net with 4 trainable layers, a convolutional layer with 8 3x3 filters and ReLU activation, a convolutional layer with 16 3x3 filters and ReLU activation, a fully connected layer with 32 units in ReLU activation, and finally, a fully connected layer with 10 units. After that, I created and trained the student, which was a simple neural network derived from the teacher model. And finally, I did a grid search for the optimal temperature and alpha values. So let's take a look at the results. Here are the teacher and student training and validation curves. And as we can see, both achieved good fits somewhere between 5 and 10 epochs. Specifically, the teacher achieved a good fit between 4 and 11 epochs, and the student achieved a good fit between 8 and 13 epochs. And after that, both started to overfit just a little bit. Here we have the teacher and student classification report. As we can see, both achieved more than 95% accuracy. And we can see that both struggled with 4s, 5s, 8s, and 9s. And overall, the teacher performed better than the student. Here we have the teacher and student confusion matrices. And as we can see, they both confused 9s and 4s, 5s and 3s, 6s and 5s, and they liked to call 2s 7s. But overall, they had relatively similar confusion patterns. And finally, we have the grid search results. And there's a lot of information here. So first, we can see that the distilled students achieved between 95.7 and 96.8% accuracy. Second, we can see that the accuracy was roughly constant when temperature or alpha was 1, but otherwise accuracy decreased when temperature increased or alpha decreased. And overall, this is not what I expected to see at all. So let's talk about it. The student was derived from the teacher by removing the convolutional and max pooling layers. And this setup is merely a self-distillation, which is when the student and the teacher are the same, while still compressing the teacher, which is perfect for knowledge distillation. Additionally, both achieved good fits and showed similar confusion patterns, while the teacher performed better than the student, which is also perfect for knowledge distillation. And finally, during the grid search, the accuracy was roughly constant when the temperature or alpha was 1. And this makes sense because when the temperature is 1, the shape of the distillation loss function is the same for all alphas. And when alpha is 1, the argmax of the student predictions is the same for all temperatures. However, accuracy decreased as temperature increased or alpha decreased, which is the opposite of what I expected. In fact, the alphas of the best distilled students were 1. And as a reminder, an alpha of 1 means that we're only considering the cross entropy loss between the student predictions and the true label. So we're ignoring the teacher predictions altogether. So what happened? Well, underfitting is unlikely since the student achieved a good fit on the true labels and the teacher performed nearly perfectly. And underfitting is also unlikely since the accuracies of the distilled students were worse than the student alone, but a bad search space is possible if the optimal temperature is greater than 10. Overall, I'm not really sure why we got this result. But in conclusion, I aimed to successfully implement knowledge distillation with MNIST, and I expected the distilled student to be better than the student alone. But I found that the distilled student was actually worse. And this result was surprising, or it was unexpected, but it wasn't surprising. And in fact, many papers have reported similar conclusions, and you can see some pictures of those at the bottom. To be clear, despite the title of my paper, knowledge distillation does really work, but it's just very difficult to achieve, and there's obviously still a gap in our current understanding of knowledge distillation. Nonetheless, it remains an active area of research, and I look forward to trying new knowledge distillation techniques in the future. And that's everything that I have. Here are my references. And thanks so much for listening.